Hello everyone and welcome to our 13th lesson, the exponential functions. Today's lesson will be, again, slightly shorter because it is mainly a building block for the next lesson, the logarithms and logarithmic functions. And this one is just a setup, so next time we can truly cover it. And the next lesson will also be delayed for a week. Hopefully that's all the delay there is and nothing more, due to my leave of absence, during which I cannot physically record or edit my videos. But without any ado, or adding to the distance of the video artificially, let's get right ahead into it. So what even are exponential functions? When someone says something is exponentially increasing or decreasing, it means that the time or input variable is in the exponent, so the output will be significantly greater or lesser with each increment of x, or time. So as we see, our function can be written as some k multiplied to a to the power of x. Of course, we can ignore k for now, as that is basically the transformation, and they are needed for behavior of the function. Not to give you the wrong idea, just like all previous functions, transformations apply the same way here. I just won't go over them again, since we covered them on pretty much all functions so far. Now, we have a few conditions for this a here. It must be greater than 0, as 0 to any power is basically boring, and it cannot be 1, because again, 1 to any power is boring. So unlike how in the power functions x was raised to some power, the input variable here is the exponent over some constant. Due to the nature of multiplication and exponents, we have two possible cases. Well, technically there is 4, but sets of 2 give the same result. I will explain why that is in just a bit. So, to be entirely correct, there is only 2 different cases of how a graph is shaped. That is based on the value of a. First example is when a is greater than 1, the function will increase as x increases. Graph will pass through point 0,1 and rise rapidly. However, when a is lesser than 1 and greater than 0, the function will be decreasing towards 0. This all ties back to one of my first videos where I said that multiplying a number with itself, so squaring, cubing, etc., is distancing it from 1, and taking a root is approaching 1. This means that anytime a number is greater than 1, multiplying it by itself will go towards infinity, and when it's under 1, multiplying it by itself will make it smaller and smaller down to 0. This will be very handy in statistics when we work with percentages, and especially in limits, which I think are coming up quite soon as well. But yes, for that point you have to look at the first quadrant, so top right, and a is like a fixed value, so it's just the behavior that we're watching. It's gonna rise up, so this point will be fixed no matter what, so 0, 1. The higher the base, the more steep the exponent's probably gonna be, but the x here, if it's positive, we can see how fast this number, like the y value, increases. It just jumps up towards infinity. Here, while a bit slower, it still approaches 0. Now for properties, the first one is that when x is 0, the output will always be 1. Well, if we have no transformations affecting that, of course, as we know that transformations affect all conditions and function behaviors. Regardless of the a value, any number to the power of 0 equals 1, and 0 to the power of 0, well, let's not complicate it and just say that technically the value of 0 to the power of 0 approaches 1, and leave it at that, because that's like a whole ass debate in mathematics. You could say it's 0, you can say it's undefined, you can say it's 1. For the sake of this, let's say it's 1, okay? Or that it approaches 1, or roughly 1, estimated to be 1. We aren't dealing with those types of problems here. The domain of the functions is all real numbers, as the exponent can be any real number. The range, however, is limited to the interval between 0 and infinity, while also being affected by transformations like moving it up or down for a bit. We also have the horizontal asymptote at y equals 0. These are the main general properties. Next one, while it isn't really a property, it is the behavior when exponents have different signs. So when x is greater than 0, so the exponent has, the value of the exponent is positive, like this, so we see it's a plus x. We see that it goes up, so we remember this graph from before, but the y will be exponentially increasing. However, when x has a negative sign in front of it, let's say that we have a formula in which the exponent would be minus t, so that would mean that the time is the independent variable, and we put in minus in front of it, most probably to show that we're working with something that is shrinking or reducing or decaying with time. So minus x in the exponent would look like this on the right. But again, this seems familiar, doesn't it? Well, the graph on the left will be adjusted to look like this one that we are already familiar with. So you see, I changed the graph to our previous example, with a being between 0 and 1. We see that the graphs are identical. Like, look at the points. This one is like -3 is slightly over here, -3 is slightly over here, it touches here on 5. So yes, but that's the property we are already familiar with. When the exponent is negative, so let's say a to the power of minus x, we can rewrite that to a to the power of x, which is in the denominator, so 1 divided by a to x, which makes these two the same, because if you put this one in the denominator, you get 1 over 2, where 2 is put to the power of x. So now we know that if only one of these, this is super important, only one of the following conditions is true, our graph will be decaying. The conditions are that a is between 0 and 1, and that x has a minus sign in front of it. If both of them are true at the same time, or none is, then the result is the other way around. This is why I mentioned 4 possible cases where there is only 2 different, but don't worry, this isn't as important to remember. This is just a helpful summary of this property of exponential functions, or whatever the other word for the property would be. So just remember this. The function will be decaying if only one of the following conditions is true. Either our a is a fraction or a value between 0 and 1, or if the x is negative, while a is greater than 1. Okay? Hopefully this stays with you here. Now, just like with linear and quadratic functions and their corresponding equations, we also have exponential equations, which you will see more often in physics and chemistry, and on some examples later, but unfortunately we can't cover them just yet, as we haven't learned the most important thing that helps us solve it all. So I will reserve that for the next lesson, so yeah, you don't have to do math today, but we can jump ahead on some applications and see where this is actually happening in real life. So this is one of the more realistic and everyday applications, which is the compound interest, which is basically a formula to calculate the future value of an investment or a loan, accounting for the interest earned on both the initial value and the accumulated interest from previous periods. So something like sequences where you could calculate nth term through 0th term and a certain ratio to some exponent, or even just any previous term and the ratio raised to the power of corresponding difference between the position of the terms. So this is the formula, the general formula for this. F represents the future value, so the value at the desired time. X represents the present value, so the starting value if you use the starting one, or the value at the current time, but we have to adjust the time correctly for that. I is the interest rate, which, while it's given in percentage values, so like 4% interest, for the calculation we have to use the decimal values, so basically dividing the percentages by 100. N is the number of segments or periods per year, so we have 4 payments a year, N would equal 4. And T is just the number of years between the present value and the time at which we have the future value, which kind of makes sense. So we have the initial value plus a certain interest. We would just multiply the interest to this value, but that would only increase this, not itself. I hope this would only give us like the value, not the addition, if that makes sense. And then n times t means how many times it's applied from now till like the desired time. So if the interest is applied 4 times a year, then you have 4 times years, kind of like something like that. But yeah, usually the time is the variable that, so the time is changing and we are observing how the f value increases with time. We could also turn this around to see how much we have to invest to have a certain value after a certain time, or how long we would have to be investing from a starting point to get a certain value. For instance, starting investment is 100, and then how many years would it take for us to reach 1 million? And then again, this is the part of the next lesson because we haven't learned that just yet, how to get the exponent out of here. The next application or appearance is population growth, where in biology, if a species like bacteria, animals, and even humans has unlimited resources, their numbers will grow exponentially. This is the easiest way to observe this is maybe with crops or bacteria populations, and even rabbits. Fun fact, the best historic representation of this is when back in 1859, an English farmer released 24 rabbits into the wild in Australia so he can hunt them for sports. And with huge amount of resources and barely any predators, throughout certain 6 years during which farmer forgot to hunt them, the population of rabbits jumped from measly 24 to an estimated of was it 200? No, it was 22 million. So 24 to 22 million in 6 years. But yes, that took roughly 100 years for the growth of the population to be shut down by a virus that finally calmed down the numbers in like 1950. Then microevolution hit, so rabbits adopted to be immune to the virus, and then the virus stopped being as lethal. And then the population reached a sort of equilibrium where the population persisted relatively constant, but much lower than the peak like years ago. So natural balance hits again. But you see, it took 6 years to go from 24 to 22 million. So that's something to put into perspective how exponential growth works. Third example is that in physics and chemistry there is something called a half-life, which refers to the decay of an element that, if simplified, states, on an example of course, for instance, carbon-14 has a half-life of roughly 5,730 years. So if you started with 100 grams of carbon-14, after one half-life only 50 grams will remain. So here the exponent would be negative, as that is a decay. And the point, so 5,730 years, represents when half of the material disappeared. Well, when we will get more accurate regarding this terminology and everything when we cover it. For now it serves as one of the examples, so I won't go too deep into correct words and maths behind it. Just so you know, half-life refers to the time after which half of the population of atoms or mass would simply disappear. That's the oversimplification. Exactly what happens, we will get to that when we cover it in chem. That's physics, I think. I'll see how I order them in that chapter. But yes, just remember the decaying graph. Half point is when that reaches 50%, so that's relatively early. Honorable mentions, as with all math, Euler has once again left his print here. The Euler's number, marked with lowercase e, which is an irrational number with an approximate value of 2.718, etc., is one of the most commonly present bases. So e to the power of something. It is also known as the natural constant or natural base, or Napier's constant or Napierian base. The other two aren't as important to know, they're just fun facts. But why is it called natural? Well, it's not due to its connection with natural numbers, but due to how often it appears in nature. Most common examples, and the ones we'll probably cover at some point, are with radioactive decay, the change in temperature of an object, distribution of heat throughout the material that we're looking at, the probabilities, quantum mechanics, even trigonometry, which is in math chapters, so we will run into that actually soon. I think in under a month, so you will see this number a lot more from now on. And of course logarithmics, so logarithms, next lesson, yes. It's either in the form of an exponent, so e to the power of something, or more often in the form of logarithms, which again, next lesson. Thank you all for tuning in to today's short lesson. Here is the mini test. I wish you the best of luck solving it. It's not anything hard, it's not anything long. It's just something simple to freshen up on the knowledge to see how much you picked up on the lesson. As I said before, next video will be delayed by hopefully at most a week. But yes, after that we will resume our schedule and we will be back on track. Thank you so much for tuning into today's video, and I'll see you all on our next quest. Bye!